In this video, we're going to look at moments. The moment of a force is a measure of the turning effect produced by that force about a fixed point. We say now that the moment about a fixed point is the force multiplied by the perpendicular distance. The unit that we use is Newton meters. So let's look at a real-world application. We've all been in the position where we've tried to push a door open. What we have then, let's say that P now is going to be the hinge. If we stand close to the door hinge and we try and push, we know that this is going to be quite hard. If we move further away, close to the door handle, it becomes easier. Let's say that this is a distance now of 0.1 meters, and this is a distance now of 1 meter. The moment of the force about this fixed point P is going to be the force multiplied by the perpendicular distance. So let's go ahead and say that this is going to now be F. If we look and we would say that we were taking moments about P, we could see the value would be F times by 1. So if I write now here moments about P, so moments about P, we could see that this is going to be now the force, which is F newtons, multiplied by the perpendicular distance, which is 1 meter. So this would give us now F Newton meters. So that is the value that we would achieve. Now let's consider if we wanted to have the same turning effect by standing here. We would have to ensure to get the same value, F Newton meters, that this would have to be 10F. We can see from here that now 10F multiplied by 0.1 would give us now the F Newton meters. So we can see that if we are 10 times closer in this particular case, we need 10 times the force. And this shows us now the turning effect of a force. And this is what we call the moment of a force. Throughout the video, we're going to work with some basic examples. And I'm going to try and take as many back to real life situations, as it's quite an intuitive topic. You can see quite clearly from here we need a lot more force to get the same turning effect of a door. And we can show that by taking moments about this fixed point P. The moment now is the force times the perpendicular distance. Now the convention is when we're taking moments, anti-clockwise moments are going to be positive. So we can say if we're going in this direction, these are positive, and then if we're going clockwise, these are negative. So we've got now positive, and this is called the sense of the moment. The sense of the moment we say now, but it will be positive if it's anti-clockwise and negative if it's clockwise. So let's look at this in action, and let's look at some of the terminology that we might use. So what I'm going to do is just model up a situation. So we'll have now some point P, and this is going to be a fixed point. So if we were doing this particular question, we would say we'd take moments about P. Now I'm going to start off with this moment right here, and what we're going to have now is some distance, and we're going to have this distance from P, and that is a perpendicular distance. Perpendicular as we're at 90-degree right angles. So let's put a 90-degree right angle just there, and we'll say now that this is going to, let's say this is going to be 8 newtons. So this is an 8 Newton force, and this now is a distance of 2 meters. We can see that this is going to be a clockwise moment. So the value is going to be negative. The magnitude we will just give as the numeric value, but in terms of the sense it will be negative. So we can say moments about P. So if we take moments about, and this is the terminology, moments about P. We've got now the force multiplied by the perpendicular distance. So force multiplied by distance. So this is going to be 8 multiplied by 2, which is going to give me now 16 Newton meters. This is simply now the product of force times by distance, hence now our unit. This is the magnitude. If we wanted now the sense, we would just say it's minus 16, as it's going to be clockwise. Let's look at another scenario. Let's grab up now an anti-clockwise moment. So let's go this way around, and let's get some fixed point P. So let's put P just here, and we will now put a perpendicular distance. So let's go ahead and just model this up, and we'll say now that that's a perpendicular distance of, let's go for 3 meters. So we've got 3 meters, and we've got a 5 Newton force. So moments about P, we would say it's a force times the perpendicular distance. So it would be 5 multiplied by 3, which would give us now 15 Newton meters, and that would be a positive value as we are going anti-clockwise on that one. Now in general, what we can say is the following. If we have a force, let's grab up a force, and we'll take this force right here, and we've got some fixed point P, which is a distance of D away from that force. So let's go ahead and put this on. So that distance now is D, and we're at 90-degree right angles. Let's just move that into place. What we can say is the following. If this now is a force F, and this is D, if we take moments about the point P, we can say now that this is going to be FD Newton meters. So force times the perpendicular distance. And that's nice and straightforward. Now, it won't always be the case that we've got this perpendicular distance. Using basic right angle trig though, it's fairly straightforward to find that. So let's have a look at a situation like that. Now what we might have is the following. We might say have a 15 Newton force. So let's go ahead and put this 15 Newton force here. And we might want to take moments about P. Now in this case, what I'm going to do is just put this here. And I'm going to have a distance that isn't the perpendicular distance. So what we might have is this situation. So we can see that these are not perpendicular. So let's just extend that out a bit and we'll make that a little bigger. So that isn't the perpendicular distance. Let's say this was at an angle, and let's say that that angle, it doesn't, let's say that's 30 degrees. Let's just make up a value right here, and let's say that this force is going to be 15 newtons. We will give this a distance, let's say this is 10 meters. What I'm going to do now is get a perpendicular distance, and that perpendicular distance, if we consider it, is just coming across here, okay? Now all I'm going to do to find that is use basic right angle trig. So what we've got is the following scenario. We want the perpendicular distance and we've got this little triangle. So this right here is going to be a 30-degree angle. So we've got this 30-degree angle. We've got now the following. We want this distance right here. So all we're going to do is simply work out what this length is going to be. Now, in this situation, we've got 10 meters, and 10 meters is the hypotenuse of this right angle triangle. We've got the right angle just here. We've got this 30-degree angle here, and we're looking for the opposite. So we know from our basic right angle trig, we can say that the opposite is the sine of the angle multiplied by the hypotenuse. So this would be 10 sine of 30 multiplied now by this force, and that's all that's doing. 10 sine of 30 is this length right here, multiplied by 15, and that will give me now the moment, if we're taking moments, about P. Sine of 30 is one of our special angles. Sine of 30 is a half, so 5 multiplied by 15, so that's going to be 75, and that will be Newton meters. Now, looking at the sense of this, this is going to be clockwise, so it's negative, or the magnitude, the absolute value, is just 75 Newton meters. Let's look at another scenario. Let's go for another one. Let's take a different one, and we'll put a point up here. Let's grab this up, and we can spin this round, and let's point back in that direction. So this time we might have now some distance. Let's say this distance right here is coming over here. Let's go for that, and let's say that this is going to be a 60-degree angle. So what we've got then is the following. Here's a 60-degree angle. Let's say that we've got some distance right here, and let's say that that's going to be 3 meters, and let's say this is going to be 6 newtons. So what we're after now is the perpendicular distance. So all we're going to do is just model this up. The perpendicular distance is going to be 3 sine of 60 degrees, and that will give me that one right there. So what we'll have is the following. We'll say now that this will be 3, that's the hypotenuse, sine of 60 degrees multiplied by the 6 Newton force, and this will give us now the value of our moment. So we're going to have 18 sine of 60 degrees. Sine of 60 is one of our exact values. It's one of our special angles. If you don't know, it's perfectly fine. You just put it in a calculator. That's going to give us root 3 over 2. So we could say that this would be 9 root 3, and that will be Newton meters. And again, this is going to be positive as it's now an anti-clockwise moment. What we can say in general, and I'll just model this up, if we have now some value right here, and what we'll do is just put this on here. Let's go this way. Let's say we've got some fixed point. So let's put our fixed point here. And this is the generalization. Let's put this like so. So let's say that that isn't going to be now perpendicular, and we've got some value right here. This is going to be theta. This is going to be a distance from now the point P to the force, and this is going to be some force. We can say if we take moments about P, this is going to give us now FD sine theta, and that will give us the value. And our units are in Newton meters. So nice and straightforward, nice and logical. Okay, let's move on and look at something slightly different. Let's go back to another real world situation and look at a playground. Now, if we looked at a playground, we might have a seesaw. So let's go ahead and just model a seesaw. Now, in terms of my modelling here, I'm not going to put on all of the forces that we would expect to see. I just want to do something that you can actually relate to. Now, what I'm going to do is put someone here, and they're going to have a mass of 40 kilograms. So if they got a mass, and let's say they can go just here. Let's say they've got a mass of 40 kilograms. That means their weight acting down is going to be 40 G newtons. Okay, so let's go ahead and do this. Let's say now we know from previous videos that weight is equal to mass times gravity. So we might have a boy sitting here, and he might have a mass of 40 kilograms. Therefore, he's got a weight of 40 G newtons. Let's put his younger brother over here, mass of 20, so he's going to have a weight of 20 G newtons. Let's say that this is going to be 1 meter from the pivot just here. We'll have now 1 meter, and let's say this is going to be 1.5 meters. We do actually have a normal reaction force here, and taking moments about P, we would call P the pivot. That means that because now the perpendicular distance is 0, it essentially can be ignored. If we think about this now, if I put, later on we will model this up, I was trying not to go here, but ultimately what we have is this normal reaction force. Okay, but because this is a distance of 0 away from the point we're taking moments, quite clearly if we multiply it by 0, it's going to be 0. Let's think about logically what's going to happen. I've got this lad sitting here, and he's 1 meter away, and this one here, who is lighter, a further distance away. Now what we can do is take moments about this point. Now if we think about the turning effect right here, this is going to be going anti-clockwise, and this is going to be going clockwise. We can look now at the sum of the moments. So if we look at the sum of the moments, taking now this direction right here to be positive, we're going to have now positive, and then we'll have the force, which is 40 G, so 40 G newtons multiplied by the perpendicular distance of 1. Now if we consider this one, this is going to be a minus value because we're going clockwise. We're taking moments about this point, and I'm going to call that point P. So if we have this fixed point coming this way, it's going to be now positive, going this way it'll be negative. So we've got 20 G, and we're going to multiply that now by the perpendicular distance of 1.5. So that gives me 40 G minus 30 G, and that gives me now 10 G Newton meters. So what does that tell me? Well, that tells me now that we're going to be spinning round. The turning effect is going to move this round. And let's just see if I can just group this up and just spin this around a bit. Let's group it up. So what's going to happen then? We've got now this resultant value of 10 G Newton meters, which means that we're going to be turning in this direction. So this is going to spin round this way, and hence he's going to hit the floor. And we've seen that before. When you've jumped on, that's what's happened. Now, if this value had been negative, we would have got the other scenario where this one would have gone. Because now the resultant will give us a negative value such that we're going to now rotate about P clockwise. So that's an everyday situation where we can see moments in action. All I've done is simply now taken the sum of the moments, okay? And that's what we've done. We've just gone ahead and done that. So if we look at something, let's look at another situation. Let's go ahead and look at this. What you'll see now, if we had this scenario, let's go ahead and say that this is going to be another seesaw problem. Let's say that we had now the weight acting down, and let's say that this is going to be, 60 G. So the person sitting here, 60 kilograms, their weight is going to be 60 G newtons. If we had now this person just here, and let's just crank this up a little, let's move them in a little, we'll move them in just a bit, and we'll put these out here. Let's say that this person has now a mass of 30 kilograms, So their weight acting down will be 30 G newtons. We'll have the normal reaction force here. We'll call this point P. I'm not going to put the normal reaction on, as we will look at that later. Let's say that this is going to be 1 metre, and let's say this is going to be 2 metres. Now, if I consider the clockwise moments about this point, we're going to have now minus 2 multiplied by 30G. If we consider the anti-clockwise to be positive, we're going to have now 1 multiplied by 60G. So what does this tell me? Well, that's 60G and that's 60G. So this is going to give us 0, and we end up with the scenario where the sum of the moments now is 0. That means that we're in equilibrium. So if the sum of the resultant force is 0, the sum of the moments is 0, then this is going to remain in equilibrium. And that will become the crux of many of the problems that we look at later. So if we can say the resultant force in any direction is 0, and we've got now a sum of the moments to be 0, then we're going to have no movement. And you can see these now are balancing perfectly. So if you want to think about this as the seesaw again, if you walk in, if you're slightly heavier than your friend, if you walk closer, there'll come some point, and I've made the numbers work, such that you are balancing. We can extend this to some basic problems. So you might be asked to find the sum of the moments about a certain point. So let's go ahead and model something up. So this is more likely, say you were given a point P, let's put this point P here, and we were asked to find the sum of the moments about P. Now this just leads on to something a bit more work in terms of these problems. So let's say we got some forces acting, let's just put some force on. So I'll kind of make them up as I go, and let's put one in this direction. So what we've got is this scenario. So I'm showing now that the anti-clockwise ones are the yellow ones, and the clockwise one, let's put this the other way around. No, we'll leave it like that. We can see all of these now, and we'll change the colour. Let's change the colour. We can see now that all of these are going to be anti-clockwise. So let's change that. So in fact, we'll do this one. Let's go for that one instead, to make this slightly more interesting. Let's say that we've got now, this is going to be 1 metre. Let's say this is going to be 2 metres. And let's say that this is going to be, a total here of 3 metres. So that's in the middle. What we'd have, let's say we had 25 newtons here, let's say that we had 5 newtons here, and let's say that we had 10 newtons just here. What we'll do is look at now the sum of the moments. So we're taking now moments about P. So we would say moments, so let's say moments about P. Okay, moments about P. So if we consider now these anti-clockwise moments, this distance right here, and this distance is going to be 3. So what we're going to have then is the following. We're going to have 3 lots of 25. Force times the perpendicular distance. Plus now, this is again going to be an anti-clockwise moment. Plus 1 multiplied by 5. And then we consider this one right here. Now what we'd have is the following. We'd have that this would be minus, and then we're going to have 3 times by 10. So what's that giving me? 75 plus 5 minus 30, and that's going to give me now 50 Newton meters. So again, this is telling me that we're going to be coming this way, and now the result or the sum is going to give me now 50 Newton meters. The fact that that's positive tells me that I'm coming this way. And of course, we could get all manner of different configurations. And it's, as stated, it's entirely up to you on how you want to do these. Many of these problems are fairly straightforward. You might even see something like so. So you might have this one right here. But if we look at that one, if we're taking it back this point, that too is going to be an anti-clockwise moment. So if you wanted to think about this now, someone's pushing. Let's think about this now. Let's just model something else up. Let's go now and we could look at a door. One of those revolving doors. When you go to a swanky building, people have revolving doors. So you might get someone pushing in this direction. You might get someone pushing now in the other direction. And we would have something like this. So if we push now, we'd look at the turning effect about this point P, and we could see who's going to win by having now the largest of these moments. So if we could push now anti-clockwise, and that would be more, then we would end up pushing now against them. So that's yet another application of this. Let's look at a scenario where we don't have, let's have a look at something else. Let's say we've got now 2 forces. Let's go for a force. And I'll do one of them as a perpendicular force. So we'll have now a perpendicular distance. Let's look at this scenario. Let's say we've got now this point P, and we're going to look at the sum of the moments. Now what I'm going to do is, this time I'm going to have now something looking like this. So let's model this up. and this is going to be another force. So let's put this force on here, and we'll just increase this. So the fact that I'm increasing it doesn't mean that necessarily the force is bigger, it just means I can get this perpendicular in. Okay, so let's see what we've got just here. Now, if I consider that this one is going to push in this direction, this is going to give me a clockwise moment, this is going to give me an anti-clockwise moment. So if we spin it about this point, let's just group all of this up. Let's go ahead and group that. What we're looking at now, if we consider this one, if I'm pivoting essentially about that point, we're going to get this. This is what's going to happen. Yes, that won't move as such, but that's what's going to happen. If I'm pushing now with a very large force in this way, we're going to come around here, and then if I'm going that way, it's going to go around there. So if you're often struggling to think which is clockwise, which is anti-clockwise, just think, if you put now a pencil in that bit and spun it, that's going to kick that one round that way, and that's going to go around that way. So let's go ahead and look at a scenario. Let's just put now a perpendicular. So that's a perpendicular distance to the force. Let's put on some values. Let's say that this is going to, let's just say that's 60 degrees, okay? Make the numbers work quite nicely. And let's say we got some force and we got 8 newtons, okay? And we had over here, let's say that this is going to be 10 newtons. And let's say we've got a distance right here. These are not drawn accurately. I'm just putting numbers on. Let's say that this is going to be 4 meters, okay? So let's now look, and if we consider the anti-clockwise moments. Now, what we've got here, I want this perpendicular distance, and that's going to be 5 sine of 60. So what we're going to have is 5 sine of 60 multiplied by 8 minus, now we've got this, and this again is going to be this is going to be the clockwise, and that's going to be negative, hence why I'm using the negative. This is just looking at the sense of the moment. This one is going to be now 4, that's a distance, and then the force is going to be 10. So what's going to happen here? Now that's going to give me 40. Now the sine of 60 degrees is root 3 over 2. Again, you can put that in a calculator, minus 40. So what's that going to give us? That's going to give us 20 root 3 minus 40. Now that's going to be, that's going to give us a negative value. So whatever this is, root 3 is about 1.71. In fact, let's put this for the calculator to get an exact value. Okay, let's grab this up. So what we got then is 20 root 3, and we're going to subtract away from that 40. Now what this is telling me from this is that this is minus, let's say it's minus 5.4 newton seconds. So it's minus 5.4, sorry, newton meters, I should say, not newton seconds. What that's telling me is ultimately that we're going to now, with all of these forces in action, we're going to actually be coming around this way. So we're going to end up now rotating clockwise as we've got a negative value. If this has been positive, we would have been rotating anti-clockwise. So that's a nice little scenario where we don't have these perpendicular forces. Okay, let's look at some more work in equilibrium. Let's say we've got some model, and I'm going to just sort of skirt around a few things, but hopefully show you some idea of what's going on. Let's say we've got some pivot, okay? Let's say we've got a pivot, and the pivot's going to be just here, okay? And I'm going to put now some force over here, and we're going to have F newtons. Let's say that's F newtons. We'll have a normal reaction at this pivot. Now, the good thing about this is, if I call this R, when I come to solve for my one unknown, if I take moments about a point where I've got an unknown, I can essentially eliminate it from my workings because, again, the perpendicular distance is 0. So let's say we've got this point P, okay? This is going to be point P, and we would say now that this is the normal reaction, or if you like, RP. So what we've got is the following situation. Let's go ahead and look at this. So what we would say now is the following situation. We would have, let's say we got now a 10 Newton force there, and we got now a 20 Newton force just here. Okay, what we're going to do now is look at the value, and we'll say that this is going to be F. Let's say that this is going to, let's say that this is going to be F newtons. Let's say that this is going to be 10 newtons, and let's say that this is going to be 20 newtons. What we want to do now is let's just give these some distance. Let's say that's going to be 2, let's say that's going to be 1, and that's going to be 1. So these are meters. What we want to do now is consider the value of F such that this is going to be in equilibrium. Now, if it's in equilibrium, the sum of the moments will be 0. Or if you like, you can set this equal to each other. So if we consider now taking moments about P. So if I write now moments, so moments about P. So about P, hopefully that looks, there we go, about P. Now let's consider the anti-clockwise moment. So this one right here. What we've got then is 2 F. Okay, now if this is in equilibrium, it will be equal to these. Now you can say that this is going to be 2F minus this one is 0, or you can just set them equal. So we've got now 1 times by 10, and then we've got plus 2 times by 20. So what we've got then is the following. We can say that 2F will be equal to 10 plus 40. So that's 50. So F is going to be equal to 25 newtons. And that's what we've got. Now, if that's the case, we could say if this is an equilibrium, F is 25. Now, also for this to be an equilibrium, we've got to consider this normal reaction force up in this direction. But quite clearly from our work before using Newton's second law, we've seen if we resolve upwards, for this now to be in equilibrium, i.e. there's no resultant force, F must be equal now. In fact, let's go the other way. Let's say RP must be equal to F plus 10 plus the 20. So this is simply saying that if we've got some normal reaction force, we can say now that RP is going to be equal to 25, which is F, which we just found, plus 10 plus 20. So that's going to give me now that RP will be equal to 55 newtons. So you can see I'm kind of making these up as we go, but you can see the problems that we can do using this. So we can say for this to be in equilibrium, the sum of the moments will be 0, and now the resultant force in all directions is going to end up being 0. And these are the problems that we're going to look at when we do exam style questions. Okay, let's look at modelling an exam style question. Okay, we won't do anything too crazy as I'm going to save that for a later video. What I'm going to say, let's just say we've got some seesaw. Let's take a seesaw, and we're going to say that the seesaw AB is going to be 6 meters. We're going to say it's a uniform rod, and we'll look at the uniform rod in a later video in more detail. Uniform essentially means that the mass acts at the centre. It's evenly distributed, so we can model its weight acting down at the centre of the beam or the rod, whatever we want to call it. So we'll say AB is going to be 6. We'll say that there's a pivot now, and the pivot will be such, and let's just say that CB will be equal to, let's go for 2 meters. Okay, so we've got a uniform rod. We've got this uniform rod AB, 6 meters long, pivot at CB. Let's just say, a girl of mass, let's say 50 kilograms. Let's say that the girl of mass 50 kilograms is at A. Okay. And let's say now the uniform rod, let's say that this is going to be 30 kilograms. So uniform rod, 30 kilograms. And let's put a boy, let's go for a boy, and we'll put the boy at B. Okay, so the boy, and let's say that he is 70 kilograms. Okay, and what we want to know is essentially what's going to happen if we model this up. So let's go ahead and model this. So what I'm going to have then is the following. Now, this is going to be a uniform rod. Now, if it's a uniform rod, the weight is going to act now down in the middle. Weight is mass times gravity. So what we're going to have is something looking like this. And this would be 30G, okay? So this is going to be 30G newtons. So let's label this up. So this is going to be A, this is going to be B. Now we've got a pivot, and we could model our pivot like so. The pivot now, C to B, is going to be 2 meters. So let's put that just there. Now at this stage, we're going to have a normal reaction force. The normal reaction force will be perpendicular to that point right there. So here's P. Let's call this P, and this is going to be the pivot. So this is going to be the normal reaction RP. So this distance right here is going to be 2 meters. So therefore that's going to be 1. So if this is a uniform rod of length 6 meters, we've got the weight acting down in the middle. So that's 3 meters. And this is going to be 3 meters as well. So we've got this point. Let's put our pivot here. In fact, we got the pivot. Let's call it C rather than P, as I've defined it to be C. Let's do that. So this is going to be RC. Okay, so this is C. We've got now, and let's consider the girl. The girl is at A. So let's put her in this direction. So let's put that just there. There's the girl. She's got now a mass of 50 kilograms. So her weight is going to be now 50 kg. So this now needs to be 50g. So weight, let's just put here, weight is equal to mass times gravity. So 50g, if she's 50 kilograms, she's going to have a weight of 50g newtons. Okay, and we can do that. Let's go ahead and do that. And then we'll look at the boy. The boy is going to be now over here, and the boy is going to be at B. So that's going to be just here, and we'll model him up. So straight away, we've got this model, and this is going to be, let's say that this is going to be 70g. Okay, we want to consider what's going to happen here. Okay, now if we look at this, we want to know what's essentially when these guys let go or it's released from rest, what's going to happen. So what we would do, we're not interested right now, in all honesty, about this value of RC. We can see that it's going to be equal to the sum of these right here. There's no resultant force. It's not accelerating upwards. This beam is not ending up in space and it's not ending up through the floor. So we can see now from here, we can say that RC, and this is just in general, is going to be the sum of these. So it's going to be 150 G newtons. Okay, let's consider what's going to happen. Let's think now about these anti-clockwise moments. So this distance right now is going to be 4. So we've got 4 lots of 50G. Then we've got plus now 1 lot of 30G. Now, if we've got this, we're going to subtract away. Remember, this is going to be now the clockwise moment, and the clockwise moment is negative. So 2 lots of 70G. So what happens right here? Well, that's going to be 200G. And this is going to be plus 30G minus 140G. Remember, we're working in Newton meters right here. So this is going to be now what have we got here? This is going to be 230. Let's work that out. So 230 minus 140G Newton meters. So what's that going to give me? That's going to give me now 90, isn't it? So we're going to end up now with 90G Newton meters. So this is a positive value. So let's just put that there, Newton meters. So it's 90G Newton meters. What does this tell me? Well, this tells me now that I'm going to be coming down this way right here, and we're going to be having now the pivot right here, and the girl who is sitting here is going to now be coming around this way. Now, we might have another situation such that we're asked to place a mass of some form, some force. They might extend the question in the exam. They might say, what we're going to do is now add some force such that this is in equilibrium. And what we want to do now is put this, and they might have, say, for example, 1.5 meters. So the question might say, we're going to put some force, and we'll call this now, let's call this force F. Okay, and we're going to put this now 1.5 from the seesaw pivot, and we want to know the value of F such that this remains in equilibrium. So all we would do in this particular case is go from here, we would say 3 lots of 50G plus now, 4 lots of 50G, let's write that out, 4 lots of 50G. So just using essentially this, we could say now that 4 lots of 50G plus 1 lot of 30G. And now at this stage, you could set this equal. You could say minus, and then minus is equal to 0. Or you could say then that if this is in equilibrium, so if in equilibrium, we know that the sum of the moments will be equal, or total moments will be naught. So now sum will be equal to naught, or AC will be equal to CW. Anti-clockwise will be equal to clockwise. So what we could say then is that this is going to be 2 lots of 70G plus now we've got, and we would say that this is a distance, I define that distance from the pivot to F as 1.5. 1.5F. Okay, so let's go ahead and work with this. So essentially what we've got at this stage now is that 90G must be equal to 1.5F, and then we would simply go ahead and solve for that to work out what the magnitude of this force needed to be to ensure that this was in equilibrium. So we could simply say that what's that going to be, 60G. So we'd say that this is going to be 60G newtons, and that would now be the force that we needed to ensure that this remained in equilibrium, i.e. it didn't move anywhere, if we were going to place this 1.5 meters from the pivot. So that's a typical question. I've kind of sort of made it up as such as I've been going through, so that it might be, the subtleties might not be as you wish in terms of an exam question, so the clarity might not be there, but hopefully it'll give you some idea of what you're doing. Now, this was modelling a uniform rod where the weight is acting in the centre. Sometimes you'll have non-uniform rods, such that we might have a non-uniform rod, and we might, for example, let's say this is a non-uniform rod, and we might say that now the centre of mass is here. Okay, so let's say that we have now a distance. Let's say that AB was going to be equal to, let's say AB was equal to 3 meters. So AB was equal to 3 meters. So let's say this was a distance of X from now a, and then this is going to be quite clearly 3 minus x. So all we would do is now work with x, and if I wanted to take moments about this point, I could look now and I could have another weight just here. I might have a pivot, and it's simply algebra from there. I think when we do the exam style questions, we'll look at some of the examples where we have non-uniform rods. I suppose the take-home message from this video is looking at how we take moments. The moment of a force is just measuring the turning force. We measure it as stated in Newton meters, and it's looking at now at the force times the perpendicular distance. So there's your start point, there's your intro. In the next video, we will look at some slightly more challenging problems.